Let's continue our review from General Chemistry 1 in Lecture 2 here by talking about how we might experimentally determine the value of the change in internal energy for a reaction. We'll recall that the change in internal energy, delta E, is equal to the sum of the work done plus the heat flow. And since work in chemistry is typically shown as PV work minus P delta V, we can substitute for W, so we have the change in internal energy equals minus P delta V plus Q. If we forced a reaction to occur without any change in volume, such as in a sealed container, then technically delta V, the change in volume, would be zero, which would make the work term here zero. And so the change in internal energy would simply be equal to the heat flow, Q. So the change in internal energy of the reaction can be measured by just measuring the heat energy flowing into or out of the system. An instrument called a bomb calorimeter, which is a threatening type name, but you'll see why it might be called that in a second, is an instrument where a reaction is carried out in a sealed container that does not change volume during the reaction. So you can think of maybe pressure building up in the container during the reaction, but you're not allowing the volume to change. Maybe that's part of the origin of the term bomb calorimeter. The heat flow is just then measured by monitoring the temperature change of the water surrounding the sealed container. So this is a cartoon of a bomb calorimeter, and you can see here that there's a sealed container, which is called the bomb. And in the sealed container is a sample cup in which the reaction would occur. And typically it's combustion reactions that are observed in bomb calorimeters. And remember, in a combustion reaction, you'd be taking a material and reacting it with oxygen. So you need a source of oxygen. So into this sealed container is an oxygen inlet. The oxygen inlet's not shown externally, but it's not a big deal. There's water in this chamber here surrounding the sealed reaction container. There's a thermometer to measure the change in temperature of the water, and there's electrodes to supply a spark to get the reaction going. So let's see how we might go about doing this, or at least calculating a delta E from experimental data that you could get from a bomb calorimeter. Suppose you wanted to measure the heat released, and thus the change in internal energy for the combustion of methylhydrazine, which is a rocket fuel. When you react methylhydrazine with oxygen, you get nitrogen, carbon dioxide, and water, and the balanced equation looks like this. Let's suppose you put 4 grams of methylhydrazine in that sample cup in a bomb calorimeter, sealed it up in that sealed container, and then introduce oxygen and a spark so that the methylhydrazine reacts with oxygen. Suppose you did that, and then you measured that the temperature of the calorimeter, meaning the water surrounding that sealed cup and the calorimeter hardware, increased from 25 degrees C to 39.5 degrees C. So, of course, this combustion reaction is giving out a lot of heat, and that heat is flowing into the water and into the calorimeter housing itself, and the temperature goes up, and you measure that. Now, in a separate experiment, the heat capacity of the calorimeter itself, meaning the water in the calorimeter, is measured to be 7.794 kilojoules per degrees C. You might ask, this is a random piece of information. Where did this come from? In order to determine the heat flow from the methyl hydrazine and thus the change in internal energy, you need to know how the calorimeter reacts to heat flow. And so if you performed a reaction in which you knew how much heat was flowing, a known reaction, you could measure the response of the water in the calorimeter. And basically this is saying that this calorimeter and water assembly takes in 7.794 kilojoules of heat energy for every degree C that it changes. In any event, our task here is to calculate the internal energy change, which we'll label deltaE of reaction for the internal energy change of this reaction for the combustion of 1 mole of methyl hydrazine. So to do this, we want to calculate the heat energy that's absorbed by the calorimeter, and we'll symbolize that as Q sub CAL, CAL meaning here calorimeter, heat flow from the calorimeter's point of view. We can calculate that by simply taking the heat capacity of the calorimeter that we're given and multiplying by the temperature change that we measure. So we have the heat capacity times a temperature change, which is final temperature minus initial, 39.5 minus 25, multiply by the heat capacity, and it ends up that we get Qcal of 113.01 kilojoules. So this is how much heat energy is being absorbed by the water in the calorimeter from this combustion reaction. And the sign of Qcal here is positive because the heat flow that we're looking at now is from the perspective of the calorimeter. So that would be positive because the calorimeter is absorbing heat. If you recall, we previously stated that we actually should be looking at energy flow from the point of view of the system, the reaction. So in the next step here, we have to reconcile the sign issue, and we'll just remember that the heat absorbed by the calorimeter is equal to but opposite in sign to the heat energy released by the reaction, Q of reaction. So Q of reaction is equal to minus Qcal. In other words, we just changed the sign. So the Q of reaction here, the actual heat flow for the reaction, is minus 113.01 kilojoules. And remember, that's equal to the change in internal energy for the reaction because the reaction is carried out at constant volume, and we can say the change in internal energy equals Q of reaction. Recall, however, that the problem asks for the deltaE of reaction for the combustion of 1 mole of methyl hydrazine. We just found out what it was for 4 grams. So we need to adjust for 1 mole. We can do that by taking the fact that the deltaE of reaction is minus 113.01 kilojoules per 4 grams. We're going to multiply it by the fact that 46.072 grams of methyl hydrazine is a mole of methyl hydrazine, and we get minus 1.3 times 10 to the third kilojoules per mole. Turns out that energy changes for chemical reactions are often calculated on a per mole basis. Now we will soon be expressing heat flow in chemical reactions in terms of a quantity called enthalpy H, actually the change in enthalpy, which you've seen in previous lectures. But don't worry, our discussion of deltaE and Q was not a complete waste of time. Chemists typically track heat flow into or out of chemical reactions by measuring the change in enthalpy, deltaH. Again, this is a term that we introduced as a matter of need earlier in the course. We want to define it a little more explicitly here. deltaH, the change in enthalpy, is actually just the heat flow measured under constant pressure. Remember, we can measure the change in internal energy, deltaE, when we measure heat flow under constant volume. we can measure deltaH, the change in enthalpy, if we measure heat flow under constant pressure. And as I say here, deltaH turns out to be a pretty big deal in chemistry. So let's back up for a minute and just look at the origin of this enthalpy term. The enthalpy H of a system is defined, it's just literally defined as this, as the sum of the internal energy of the system and the product of the pressure and volume. So here we have enthalpy defined as the internal energy of the system plus the product of the pressure and the volume. This is just simply how it's defined. If instead of determining the absolute enthalpies of the initial and final states of a reaction, H sub I initial, H sub F final, or as we've substituted before, initial state meaning the reactants, final state typically meaning the products. Instead of concentrating on getting absolute numbers, what we're going to do is concentrate on the change in enthalpy, deltaH, between the initial and final states, or in other words, between the reactant and product states. deltaH as being the difference between the final enthalpy and the initial enthalpy. If we rewrite our definition of enthalpy in terms of changes, it might look like this. The change in enthalpy equals the change in internal energy, that should look familiar, plus the pressure times the change in volume. Now notice we don't have a delta in front of the P because we've defined that we're going to measure this enthalpy under constant pressure. Also remember from the previous lecture and even from the previous slide in this lecture that delta E equals W plus Q, or it's also equal to minus P delta V because that's how we define W, plus Q. And so if we substitute minus P delta V plus Q for delta E in this equation, delta H would look like this. And now conveniently, these two P delta V terms cancel. There's a minus here, there's a plus here. They cancel, and what we end up with is that delta H equals Q, and now we're going to say it's Q sub P because it's the heat flow measured under constant pressure. So we'll use a little subscript capital P to show that. Stated again, the change in enthalpy for a chemical reaction or process is simply the heat flow into or out of the system measured under constant pressure. If that heat flow is negative, then delta H is mathematically negative. This is called an exothermic process. That would be the case when the final state has a lower heat energy content than the initial state. In other words, when HF is smaller than HI, the result there would be that heat energy leaves the system and flows into the surroundings. That's why everything has a minus sign here. Conversely, if the heat flow under constant pressure is positive, then of course delta H would be positive. This is called an endothermic process or reaction. In this case, the final state, enthalpy, HF, is larger than the initial state enthalpy, and so heat energy flows into the system from the surroundings. Again, that's consistent with our sign convention we set up previously. If the heat flow sign is positive, then heat's flowing into the system or into the reaction from the surroundings. Well, how would we actually experimentally determine delta H? In other words, how would we measure heat flow under constant pressure? This is actually easier than measuring heat flow under constant volume, because to a reasonable degree, you can measure heat flow under constant pressure by simply letting a reaction occur under atmospheric pressure in a laboratory. And you're assuming that the atmospheric pressure doesn't change appreciably while the reaction is going on, which is a pretty good assumption under most cases. And these conditions can be met even in a general chemistry lab with something that's very simple. It's called a coffee cup calorimeter. So let's look at an example of measuring deltaH, in other words, heat flow under constant pressure, using a coffee cup calorimeter. Well, what would a coffee cup calorimeter look like? Well, surprise, surprise, it involves using styrofoam coffee cups. So you see here two styrofoam coffee cups nested together with this cork lid on them, and the styrofoam cups and the cork lid thermally isolate the chemical reaction from the outside environment, the chemical reaction occurring in solution here. And it does not completely seal the container from atmospheric pressure. So this is not completely sealed. So it allows you to thermally isolate this reaction from the outside while allowing the reaction to occur under the constant atmospheric pressure. You can have a glass stirrer stirring the reaction in solution, and of course you're going to want a thermometer so you can measure temperature changes that occur during the reaction. Suppose a student wishes to measure the deltaH of reaction for a reaction of the strong acid HCl with some strong base sodium hydroxide. This does produce heat. It's an exothermic reaction. Here's the balanced equation that ought to look familiar. The particulars are the student mixes 50 milliliters of 1 molar HCl with 50 milliliters of 1 molar NaOH. That would mean that there's the same number of moles of each and it reacts completely. There's nothing left of the original HCl or NaOH. There'd just be sodium chloride and water. They do this in a coffee cup calorimeter, and when they do that, they observe that the temperature of the resultant solution increases from 21 to 27.5 degrees C. So the reaction is giving off heat, and the water, the solution, increases in temperature. And we just need to calculate the enthalpy change in kilojoules per mole of HCl. So what we're going to do here to do this is we're going to assume that the calorimeter loses only a negligible quantity of heat to the surroundings, that the total volume of the solution is 100. You may say, well, that's obvious. 50 plus 50 is 100. Remember, sometimes volumes do not mix additively, but in this case, we'll assume that happens. We'll assume the solution density is equal to the density of water, not a bad assumption, and that the specific heat of the solution is equal to the specific heat of water, again, a pretty good assumption. So what we'll need to do is determine the heat energy absorbed by the solution, Q of solution, in which the reaction takes place. We can do this by taking the heat capacity, which is given here in joules per gram per degree C, and multiplying by 100 grams. You say, well, where did I get 100 grams of solution? Well, if we assume the density is 1 gram per milliliter and you have 100 milliliters, you'd have 100 grams of solution. That allows us to cancel out the grams, and then we'll multiply that by the temperature change. And remember, it's always final minus initial. And when we do this, the degrees C cancel, grams cancel, we're left with joules, so we have a heat flow for the solution of a positive 2,717 joules. Well, again, we have the heat energy absorbed by the solution, 2,717 joules. We remember that the heat absorbed by the solution would be equal to and opposite in sign of the heat released by the reaction. So we can immediately figure out that Q of the reaction is simply minus 2,717 joules. And this is actually the change in enthalpy for the reaction. Since remember, heat flow, Q of reaction here, occurred under constant atmospheric pressure. But again, like the previous problem we did where we calculated deltaE, we wanted deltaH per mole of HCl, and we did not react a mole of HCl, so we need to make an adjustment. What we can do is just simply calculate the number of moles of HCl that reacted. Remember, we can do that by taking the volume of HCl used times its concentration, and that's how many moles of HCl reacted. So we can calculate the enthalpy change per mole of HCl by just taking the heat released by the reaction, minus 2717, and divide by the number of moles of HCl, and we get minus 5.43 times 10 to the fourth joules per mole of HCl. And we could convert this to kilograms, minus 54 joules per mole of HCl. So delta H of reaction here is negative because this is an exothermic reaction. The reaction causes the solution to increase in temperature. Now, just a note on notation here. Whether you see the enthalpy change for a reaction written as delta H of reaction or just delta H, the meaning is the same. Sometimes we put a subscript on there for clarity or to make it look nicer. But you don't worry about whether that's there or not. It's the delta H of the reaction. So both are expressions of the magnitude and direction of heat flow for a system undergoing a change in internal energy under constant pressure. Now, in part 2 of this lecture, we're going to look at some ways that we might be able to actually just calculate a delta H from experimental data that's been previously collected over the years and assembled into tables.